Thank you very much for the invitation. It's a great pleasure to be here. I'm going to talk about fermions in, well, twisted lattices. So what's meant there is a realization of the topological Haldane model. And then fermions also, quantum pinholes. Okay, what I mean with this is fermions in quantum point contacts, and in particular also in the interacting regime. In a sense, this story is a completely incomplete story. It's an unfinished story, and I cannot finish it because what really I would like to have, but I do not have, is a situation like this, where you have a kind of a, with cold atoms, a transport setup where you have two reservoirs and you can measure some transport, and where you can adjust interactions, maybe have strong interactions, and then in the middle have some non-trivial topology. So I guess that would be a really interesting system. But I need to disappoint you, and my talk will be, will have two parts. One part will be mostly non-interacting part about non-trivial topology. And then there will be a part about transport measurement, but with strong interactions and with some surprises, which, yeah, we also now start to find out what the reason for these surprises are. Okay, so in a non-interacting system, somehow, I mean, at least you should have a spin degree of freedom to have something. And the way we have our spin degree of freedom, or pseudo-spin degree of freedom, and we had that in the first talk today, and that in a graphene type of a honeycomb lattice, you have those two sub-lattices, which give you a quasi-spin degree of freedom. Okay, so how, and as you will see, we will also rotate this lattice, and that gives some additional non-triviality because it breaks time reversal symmetry. Okay, so just for the condensed matter physicists, so not that I suddenly start with lattices and so on. So what we have is very cold atoms, a quantum gas of fermionic potassium-40, and this gas we load in an optical lattice, which provides our periodic potentials, and these lattices have mutually perpendicular beams. So the question is now, of course, how do we construct a system with Dirac points? And the way we do it is by overlapping different interference patterns. And one way how to look at this is, I mean, those two red beams here, X and Y, they produce some band structure. And then we have this additional brown beam, which has the same symmetry. So it doesn't break, it's an important point that this doesn't break inversion symmetry. So, and then you can imagine, okay, if it doesn't break inversion symmetry, there are some states in this band structure which are also eigenstates of this beam. And this beam is now shifted with respect to the minima of that one, so that it acts on those states which are also the eigenstates of this, just by pulling the one up and the upper one is pulled down and the lower one is pulled up, but the states are not coupled. And that's how we get, in this configuration, the Dirac point. So that's one way how one can look at it, and that is the band structure that we get. Okay, and then again, a experimental point is how can we measure these Dirac points, and the idea there is that we take the cloud of atoms and we accelerate it through the band structure using a magnetic field gradient. So we had this, we talked just about the force, and of course what is happening here is either you can have Bloch oscillation if you miss your Dirac point, or if you pass through a Dirac point, then the atoms will go into the higher band. And that we can measure by switching off the lattice gradually and then doing a band mapping which maps quasi-momentum on real momentum, and the higher bands will lie further outside. So these are the missing atoms in the lowest band, and these are those transferred to the higher band. So that reflects the Dirac points. So now I said early on that we have this additional lattice which we position such that it doesn't break time inversion symmetry, and we position it by changing a frequency, so we can position it very well. And that way we can also position it such that it breaks inversion symmetry, and then you break this sublattice symmetry, and you also realize that you will the Dirac point there, a gap will open up. In a sense, you could imagine that, I mean, this superposition of momentum states when you go along this line, it has just a different phase here than that one. And now suddenly, okay, if you follow adiabatically, you have to make this phase change. And that corresponds also to the Berry curvature that you have in this region. And a way to how to measure this Berry curvature, there was a proposal by Nigel Cooper, and that is that you look at the semi-classical motion of the atoms. So if they pass at near one opened gap, then you would see a drift to the right, and at the upper one you would then see a drift to the left. I think one can look at it in a way that it's like a quantum pumping in one direction, and then at the other one it goes back again, because of time reversal symmetry. And now you can argue, okay, that a bit to the right, a bit to the left, well, it averages out, you won't see much. Okay, but then you could also argue, what would actually happen if this Berry curvature was the same at both Dirac points? Then you would move to the right, and then you would move again to the right, and that very much looks like a Hall current. Okay, so, and now of course the question is how can you engineer that, and fortunately Duncan Haldane had thought about that long before us, and he set up a model where you have a quantum Hall effect without having a homogeneous magnetic field. And the idea of that model is the following: you start off with the honeycomb lattice and with its inversion and time reversal symmetry, and now you break time reversal symmetry. And as theoreticians, you can do that by introducing, he did it by introducing some complex matrix elements, which give you complex next nearest neighbor tunneling, and arranged as it's shown here. And if you have this tunneling, then you open up two gaps again in the band structure, but now with the same Berry curvature. Now you can also, and this, if you have the situation that they have the same Berry curvature, then you also, that corresponds to the existence of an edge state, and you have a non-trivial topological Chern insulator. Okay, the whole, you can also break in addition the inversion symmetry, and then you can get the phase diagram of the Chern insulating phases and the band insulating phases. And maybe let's have a quick look. So this is the situation of graphene. And then if you just break inversion symmetry, you open up the gap, but the same Berry curvatures. If you break time reversal symmetry, then it's the same Berry curvatures, and you open up again a gap. And now you can wonder, okay, what is happening here at these phase boundaries? So let's assume we are here, have these gaps open, and now we break inversion symmetry in addition. Then one of the gaps closes, and on the transition line, it just closed one gap, and it opens up, but with a different Berry curvature. So the question at that time was how can you actually realize that? And Conductance Haldane wrote that while the particular model presented here is unlikely to be directly physically realizable, it indicates that at least in principle the quantum Hall effect can be placed in the wider context of phenomena associated with time reversal invariance. We of course thank him for this nice comment, putting up the challenge, and there was in 2009 there was the proposal by Oka and Aoki, and they made a proposal for a photovoltaic Hall effect in graphene, and the idea was that you take graphene, and then by shining in circularly polarized light, you would rotate the structure and thereby break time reversal symmetry, and then you could switch on and off a Hall effect. And unfortunately, he came visiting Manfred Sigrid, a colleague, and then he also came to our lab, so we talked, and that's how the project started. And in atoms, what you can do now to do this rotation, I mean, there are also the rotating systems in photonic systems. In cold atoms, there's this method of shaking, where you simply put piezos behind your mirrors, and then, well, you need to take care that your lattice structure remains the same, and so on. In particular, that I see Daniel here in the audience. Daniel Greif, I will be a bit careful to say that it's so easy. So you can rotate your structure. In particular, you can now also control the phase of those two mirrors. So you can either shake in phase or out of phase. And if you shake out of phase, then you get then you break time reversal symmetry, and you can, using Floquet theory, you get an effective Hamiltonian, which has this next nearest neighbor complex couplings here. And in this way, we can now do the following experiment, or in the experiment, we can produce two band structures. So either we shake in phase, and then we expect a trivial band insulator, or we shake out of phase and break time reversal symmetry. And then what we do in the experiment, then we measure again the displacement of the cloud. So we measure, we move the atoms up, and then we take an image. We can measure the transverse drift. We measure if we accelerate downwards, and then we see, okay, in this case, there should be a difference if we have non-trivial topology, whilst in the other case, that would both times should cancel. And then we detect the difference in the center of mass position. And we can do that either for just breaking inversion symmetry, and this differential drift doesn't change much, or we can do it by breaking time reversal symmetry, and here is that is the relative phase of these two mirrors, and there we can see that we see this differential drifts. And we can map that over the whole phase diagram. So here's breaking time reversal symmetry, and here is the breaking of the inversion symmetry. Yet our measurements, this blue and red, that doesn't exactly coincide with this phase diagram. So from this, we do not get the lines of the phase diagram. The reason is if the atoms are very close to the Dirac point, they also are transferred to the higher band. So then one can wonder, okay, how could one actually get the phase diagram? How could one get these phase lines? And as I mentioned earlier, these are characterized by the fact that one of these Dirac points closes. So that's if one Dirac point closes, then you have then you have this phase transition. And that we can measure in the experiment where this point is, where the Dirac point, one of the Dirac point closes. And we can do that again by this band mapping. So we accelerate these atoms, and then we look how many atoms are transferred at the upper and at the lower Dirac point, and where are the respective maxima of transfer. And that's where we locate then this transition line. And from this, we can, from such measurement, we get a phase diagram of this Haldane model. And these different, I mean, the points are obviously the experiment, and these different theoretical lines are within kind of our knowledge of our parameters. Okay, so what about interactions? I will not talk much about interactions, as I had said, but we found parameters where we could create layers of this Haldane model and where we did not, for certain frequencies, observe significant heating. So there is optimism, but we keep on working on that. So we are doing the lab now, shaking systematically what is happening if you have interactions. So that one really can find out whether the shaking is a useful tool or whether it's not. Okay, so another question one could ask, okay, I mean, this Haldane model is kind of the central part or half of the part of the Kane-Meyle model. So one could ask the question, what about spin? Can I make that spin dependent? I mean, can I create something that for one component it's oscillating one direction, for the other component in the other direction? Shall I do that again? That looks great. Yeah. Okay. So, and that one can do. I mean, you remember Monica's talk where they had applied a magnetic field gradient, and then it, of course, different spin components act differently. But now you can also do that. You could do this shaking with a magnetic field gradient. And that means that different internal spin components should see a different different band structure. And if you had magnetic moments of opposite sign, then you would just shake in opposite directions. And we did a test experiment on that. So we produced clouds of two different spin states, and we did a magnetic shaking, and then we looked at the band structure by band mapping. And indeed, we could associate, I mean, these are these mapped band structures. We could associate here that you have in one spin state, you have a flat band, while in the other one, it's still, you have still a confining band, or even you can invert one band whilst the other one is normal. So this nicely shows you that one can think about Hamiltonians which have hoppings that are different for the different spin states, which and without being close to a resonance. So I think there can be quite some more things to do. Here I would like to thank the Lattice team and the postdocs at the moment on the experiments, Rémi Debuquois and Gregor Jotsu. And of course, Daniel Greif did his PhD on that experiment, and he is now here if you have further questions. Okay, but I said in the beginning one really would like to have something like that. Okay, so now we believe that in principle something like that one can create. So the question is now, can one also create such type of transport experiments? Okay, so the starting point here is now an experiment with very good optical access. So we have this experiment for lithium, for fermionic lithium, and you see here we have a glass cell, and here in the middle is a cloud, and then we have two microscopes, so we can project potentials, high numerical aperture microscopes, so we get a resolution of 700 nanometer, and a second one so that we can actually see what we have created in terms of potentials. But the starting point is just a normal elongated lithium cloud, lithium-6 cloud, and then we shine in from the side, a TM01 laser beam which separates the cloud into two and has a two-dimensional channel in between, okay, in the first step here. So now just to tell you how we measure. So we prepare some more atoms here than there, and then we measure what is happening, okay? And we take images. So we kind of have a Fermi battery, and then we discharge it. So the atoms will flow from where there are more to where there are less. And then we get curves like this. So these are discharge curves. And you can really look at it as if you are discharging a capacitor. But from these curves, what you can now extract is this time constant. And this time constant that's measured, and the C here, that corresponds to the compressibility, which from the knowledge of our trap frequency, or measured knowledge, for non-interacting gas one can calculate. So this means knowing this, I can, in absolute values, get the conductance out of these measurements. Okay? And now using these microscopes, we can also make this channel very tiny, very small. So imagine now you have these two reservoirs and you have a hole between the two reservoirs and make this hole smaller and smaller. Then, okay, you imagine that the conductance gets less and less. And at some point you might start wonder, okay, what are the length scales if my Fermi wavelength is getting on the size of my hole? Maybe I have to take care of quantum mechanical motion. And that's indeed the case, because then you have different modes from going from here to there. And if you analyze this problem by simply taking two reservoirs and some constriction, which may be a radial harmonic oscillator, and then calculating the current as a function of some bias in the chemical potential, then you will find that your conductance is quantized, and that each conducting mode contributes with a conductance of 1/h. So for each mode, you get 1/h for fermions. So this is kind of a consequence of Heisenberg and Pauli's principle. So it's kind of robust. So we do not question too much Heisenberg. I mean, waves we do have, and in Pauli also we do not question too much. And indeed, in the experiment, we measured this conductance, and we're of course happy to see in neutral matter for the first time we could see these quantized steps. But of course, we also have to admit that similar steps in electronic systems had been measured before, and almost as nice. But then one can ask, okay, what is the difference? But I think the electronic systems, they do have problems if they want to build, as far as I understand, it's not easy for them to take two strongly correlated materials and then make a quantum point contact for two strongly correlated materials. That's, for us, of course, in particular with lithium, easier. So we can just change the magnetic field and create two strongly correlated superfluids and have this quantum point contact in between. And then we can ask, okay, what is going to happen? So, okay, so we are here right on the resonance of the Feschbach. Okay, so then one wonders, so what is happening? Okay, we measured. We didn't wonder too much at first. We measured. And the control parameter in the measurement, one control parameter is this kind of what we call gate potential, which controls the chemical potential in the region of the quantum point contact. So we can change kind of usually it would, due to the 0-point motion, potential line would go up, but we can press it down with this control beam and adjust it relative to the chemical potentials. Okay? And then what we saw are no longer exponential curves, but now what we see is highly nonlinear behavior. And these curves here, this is for a large chemical potential, so a strong gate beam, attractive gate beam, and this is for a small one. And now we can also plot that in units as a current bias relation. There again, you see a very strongly nonlinear current bias relation. And you also see these curves, and these are actually theory curves. And these theory curves, they come from our colleagues, Shun Uccino and Thierry Giamarchi, because we thought that we have this one-dimensional system between the two reservoirs. Then clearly we ask Thierry. So, however, it turned actually out that these measurements have not much to do with actually 1D physics. So the picture, how this theory works, is basically that they assume, and that's the case in our system, that we have a large proximity effect. So the wave function, the paired wave function, will kind of penetrate into the channel, and then it will couple to the other side. So basically, you need some coupling matrix between these wave functions. So you have kind of a point-like connection, and that you have per channel you have some parameter alpha, and we have either a 1 or 3 channels because of the geometry. And the mechanism, and then you might ask, the second question is, you might ask, okay, I have a superfluid here, and I couple them, okay, I will have Josephson oscillations. Well, but we measure a DC current, so it's not immediately obvious. So, but what the process is, I mean, and also you need to keep in mind that the gap is much larger than the chemical potential difference. So it's not obvious what is happening, but the process that is dominating, and that is also leading to the nonlinearity, is multiple Andreev reflection or a pair tunneling. So several Cooper pairs tunnel, and they come up with the energy, so n times the chemical potential, and then you can break up a pair. So that is the underlying mechanism which explains those measurements. And okay, I mean, I should mention also that in Massimo Inguscio's group at almost the same time, they looked at the Josephson limit of a 2-reservoir experiment. And we also can measure as a function of temperature. And as you see, these dashed lines, these look nice. They fit nicely with the data, but they are dashed. They are not theory, so they are just fits. So at finite temperature, it's a 0 temperature theory. So now you can also in the experiment change the interaction. Okay, so we could just scan on the Feshbach resonance and, for example, go very much on the BCS side with fairly weak interactions. And there we again see a conductance plateau at 1/h. And then we move closer here, and that's where we got surprised. There we saw a plateau. I mean, this is still a plateau which is higher than 1/h. So either Heisenberg or Pauli doesn't work. I'm not so sure. And then we moved further, and plateau gets shorter, but it's still a plateau or a structure at least. And further, and still, I mean, it's a structure. You may not call it a plateau. And then, of course, in some limit, you have the previous situation. Okay, so that, and then we can make a whole conductance map as a function of horizontal confinement, kind of like a split gate structure. And, well, that's just the same data, or a bit more data in a map.
This is a linear conductance?
Yes. 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 So we have no indication that it's nonlinear here. Experimental statement. And there's another aspect that we can measure. We can also measure the spin conductance. So we can make spin imbalances, and then as a function of the interaction, look at what is the spin conductance doing. And so kind of we have for one spin component a higher chemical potential on the one side than on the other side. Okay, and what we observe for the spin conductance as a function of this gate potential, that is this beam which makes the potential deeper, for almost non-interacting, we can see an increase, maybe almost steps here. So here's where the first channel opens and then the second. So it's spin conducting for weak interactions. Yet for stronger interactions, this spin conductance is suppressed, which you would expect if you have pairs. So you will not be able to bring the pair through a single particle through this middle region. And you can also make a map. So, however, I think the question is then that we had is how can it be that you have a larger than 1 over h conductance? Because even, I mean, you look at the literature, and 5 minutes is perfect, even maybe less. If you look through the literature, there were studies with interactions, but they then came to the conclusion, well, it's still 1 over h if you have kind of 3D reservoirs, because somewhere the atoms or the particles must come. You can have one-dimensional lines, and with one-dimensional reservoirs, there you can get steps which are larger. But it was not at all clear what would possibly be an explanation. And then, well, we had contact with Leonid at a conference, and then it was also really nice that Eugene Demler stayed for a few months in Zurich, so we could have discussions. And then he worked together with Martin, and he is also here somewhere in the room, I'm pretty sure. Yes, so, and I'm quite pleased about that, because I think I can give you the explanation, but surely the deeper picture he will be able to give. Okay, so what is the idea and what is the question here? Okay, the question is the following. You have this energy, so that is here the center of the point contact, and due to 0-point energy, this potential of the lowest channel looks like this. And of the higher channel, it looks like this. So if you have non-interacting, it's very clear. I mean, this will never make it through, because otherwise energy conservation is also a big principle in physics, so it will not work. And now you can wonder, okay, I do have a channel, a 1D-like system, and then one could imagine, yes, and we are strongly interacting. So you could have a pairing in the channel, so kind of enhanced pairing in the channel. That is plausible, and you should have, I mean, the channel should favor pairing. But then you could still say, oh, does that solve my problem? So it may bring another, I mean, one atom might bring another one, but not higher than 2 over h. And then, okay, you think about this channel where there are these pairs. And then, okay, you might think, okay, it might look a bit like this. Okay, you have the pairs. You might consider it as a superfluid here in this channel. And then you have some leads coming in. And now the question is, or an important point is the superconduction region, does it look like this, or does it look like this? If it looks like this, we keep on having a problem. However, if it looks like this, then we might have to count the numbers of channels that are here, and not the single channel that is here. Okay? So if it's again a proximity effect out now from the channel to the outside, and then you can have from the higher band you can have Andreev reflection processes into the central region, so not only from the lowest channel. And in these calculations, there is now calculated the superconducting gap for different energies, and these thin lines, these are the energy levels of the different modes. So you see they get, of course, degenerate when you go more into the 2D region, and then one of them is the lowest, and then the other one are the next higher one. And now the idea is that you can get up to, well, 3 bands, and from 3 different bands you can get particles into this superconducting region. And then they calculated that, and they indeed get conductances which I think have a fair agreement, or fair qualitative agreement with what we see in the experiment. And here also that's this curve for the spin conductance. And there are 2 more experimental slides. What we are, just a preliminary one, what we are now playing with at the moment is that we have a scanning gate system where we can now place a little tiny focused beam, and then we can scan over this whole region and see how the conductance changes, very much inspired by condensed matter. And then we can see they have these conductance plots, and this for non-interacting we can compare it with non-interacting theory, and we can also measure how precisely what the position sensitivity is if we change, and then we get up to a position sensitivity of 10 nanometer. So, but it's convolved, so position sensitivity. So we move one thing by 10 nanometer, which is fairly large, and then we see a change in conductance. And then, of course, we're also thinking and preparing measurements to increase the number of point contacts to, well, looks almost like a lattice. And with this, I would like to thank also the lithium team. Jean-Philippe Brantu was leading that team, and he will start a professorship in Lausanne from September on, and the postdoc now on the experiment, that's Laura Corman. Sebastian Grinner is not on this picture anymore. And, well, with this, I would also like all the other team members. Thank you very much for your attention.
For the case, if I had a number imbalance where a spin polarized PEC, which is a superfluid boson, then you would expect oscillations in imbalance, yeah?
Yes.
Okay. And then, so I guess the confusion is, so for the case where you have a superfluid of pairs, and you have these Andreev reflections, which basically, I guess, add multiple frequency components, this damps out as opposed to oscillating.
Yeah, there should be an underlying oscillation too weak for us to measure.
Okay, but it's averaged out?
Yes, yeah.
I guess I'm just a little surprised. I guess I would have thought maybe it just changes the effective tunneling. Like instead of having multiple different frequency components that just sort of add up incoherently and then you get something like the phases, you might actually just expect some new renormalized tunneling which couples the 2 reservoirs. Is there a clear way to see why that?
I think there were kind of thoughts about whether there can be phononic components, but these were excluded, which I think is similar what you suggest simply on the scale arguments. So yeah, I mean these we measure that for fairly different parameters and sizes of our channel, and but we did not change each time another alpha. So, but
you should.
Okay.
So, in your description, you seem to treat the reservoirs as though they were normal. I mean, you were talking about quasi-particles.
Okay.
So is that
Flowing fluid. So then into the normals. Have the reservoir.
Spin, or is it only transferring the spin without actually transporting an atom across?
So we measure, I mean, we produce a spin imbalance in those two reservoirs by at some stage a magnetic field gradient. And then we measure how this spin imbalance, how or whether it relaxes or not. So it is particle transport.
But in principle, you could have simple spin transport without the particles.
Yes, one would. We could not distinguish. We couldn't distinguish from the measurement, but yeah.
Maybe one last question. Is it possible to go into a Coulomb blockade kind of regime?
Yeah, it should be possible, but I wanted to discuss a bit more with Daniel on the repulsive side of, But there's still tomorrow or so, or later today. And then I can give you a better answer.
We are going to be taking, as I understand it, a coffee break now, so let's thank our speaker one more time.